And we're gonna start with Musab, who is gonna talk about the use of open web standards in a 3D visualization of archaeological data.
Hello everyone, my name is Musab Abdalla, and I will be talking about the use of open web standards in 3D visualization of archaeological data. The talk is going to be about the web application that we have made. Okay. Yeah. The talk is going to be about a web application that we have made to visualize an archaeological site. At the beginning, I'm going to be introduce the archaeological site, a little bit about its geography and stuff, and then I'm going to talk about the progress of the set of the geo projects regarding this archaeological sites and where the web application comes in the game. And then I'm going to talk about the challenges that we faced developing the application. So the site is located in the Altai mountain. It is located in the southern part of the Russian Federation, just between Mongolia, China, and Kazakhstan. And in the mountain range, it's located in the northern western part of the mountain range in Central Asia. This is the conservation park that was represented in the application. It's surrounded by the red borders, and the yellow spots represent the areas with archaeological significance. The Altai mountain region is a region that is populated mainly by Altanians, the indigenous inhabitants, and Russians and Kazakh people. It was populated by nomadic tribes for most of its history. It is known as the Scythian heartland. And the Scythian people are a nomadic culture that flourished 2,500 years ago. They didn't left behind any settlements or written documents. Basically, they have a huge territory that they occupied, and they have a strong interaction with other cultures. There's a lot of referencing for them in the Greek literature. The most evidence of their existence is that their rituals in burying their dead, they have an interesting embalming and mummification, and they have a really interesting burial mounds, and they're famous with putting treasures in their graves. This is a picture of one of the burial mounds. It's this circle with the stones on top of it, and they also have the standing stones, and these are the most famous features of their heritage. The Ush-Inmik Ethno-Nature Park was created for the purpose of the conservation of the archaeological sites. It consists of 10,000 square kilometers. It was established for the purpose of protection of the archaeological sites, to create public awareness, education, and to support tourism of the region. There is a set of international activities between Ghent University and the Department of Cartography, the Institute of Cartography and Technical University of Dresden. One of the targets of this corporation is to create a virtual conservation site in 3D for Ush-Inmik. And the motivation for this is to support the conservation and to create a web-based information awareness, and also to simulate tourism. A little bit of the history of the 3D model, or the data that the application used. There was a set of research and projects. First, there was a creation of a topographic model using the maps and geodatabase, and then using the satellite imagery, a thematically enhanced GIS model was created. Also, a GIS model with 3D consistency using the elevation data from the satellite imagery was created. Then a set of projects in the 3D modeling was conducted, and basically they ended up with creating prototypes for the fingerprints of the buildings, some recreation of specific objects in 3D, like the burial mounds. And additionally, at the last, there was a refined 3D model. And the application comes in the presentation framework. There should be, this model needed to be accessible for the public. So the design consideration for this web application that will visualize this 3D model is to create a geo model as a door for internal and external information. Also, the idea was to provide a multi-scale visualization, because when it comes to archaeology, the user might be interested in a small artifact or a big village, so we need to provide a visualization for both scales. Also, the openness for other information types, the integration of different archaeological data was ideas that to be considered. So, let's start about the application. So we started by using different vector layers, represent man-made features, natural features, and what's not. Also, we had a digital elevation model and a satellite imagery. Two different 3D models for villages was created. It was rendered in Cinema 4D. It was created, this is a snapshot from the video rendering of the scene. The idea of the application is very simple. The user will be interact in the client side with the application. Cesium is the core technology for this application. The data sits in the server side and served via different applications, the database via Node Express, and a Go server serves the terrain data, and the Apache serves the rest of the static files. Cesium also provides the ability to request web map services, and the user will be interact with the 3D model in the client. A little bit of introduction about Cesium for people who didn't hear about it. It's an open source JavaScript library for world-class 3D globes and maps. It's built on HTML5 technology, namely WebGL, and it has an engine that resembles the game engines, and this is why it actually works very good when it comes to visualizing dynamic data. This is a little bit of, this is a graph to explain the graphic stack of Cesium. Luckily, we only had to use the top layer, so we can, all of our data can be represented as primitives. We have the globe, and the globe can represent the terrain and the imagery layers. They have to be provided in a quad tree format. The 3D models are represented in a format called GLTF, and the primitive is actually the way that Cesium draw shapes, and the vector data can be drawn using as normal primitives. There were three main challenges developing the application. The first was about the 3D model. So the 3D model, it was initially designed and built to be rendered in the Cinema 4D framework, which means that it was not spatially referenced. It also is not linked to any kind of additional information. So you have blank cubes. That's basically the 3D models that we have. The other issue is about the terrain data. Cesium does not allow you to render your own terrain data out of the box. And the model was built on top of a data that has a different source than the one that used by default by Cesium. So we have to use our own terrain data. The other challenging part was the underground chambers, which is the most significant archaeological features. The problem is that they are underground, so the cameras somehow need to penetrate the terrain. And the other issue is that they are indoors, so the navigation events in Cesium are for looking from top, not within, like, they're not convenient with indoor navigation. So regarding the 3D model, as I said, the GLTF model, which is a JSON-based spec, it's kind of a JSON collada, a little, you can say. It also allows the node hierarchy, so every feature can be divided into child nodes, and the shaders and the textures can be injected within this child node. In Cesium, there is a method called scene pick. So when the user click on the GLTF model, it gives back the ID of the clicked node. So if we have a model that is segmented to nodes, we can retrieve the ID of each node that is selected. And the idea is that we will use this ID to fetch the associated data from the database and then render it in a HTML template. The model was, this is a picture of it. The model was only in one node, so we had to select all the connected meshes and segment them in an independent node. and we had to do this manually for each one. And then we gave them an ID that matches the ID that will be in the database. For the database, we just developed a prototypical database with no schema, no authentication or any of this stuff, because we just wanted to test this linkage approach. We also added a put request so that we allow crowdsourcing and test the VGI approach in this project. Regarding the terrain data handling, Cesium uses this quad tree approach to visualize the terrain data. It's like the imagery thing. When you zoom, based on the zoom level, you receive a certain tiles. There are two types of data that are natively supported by Cesium. One is called the height map, and the one called the quantized mesh. I don't have the time or enough information to explain them in details. But we have three options to use our own customized terrain data. First one is the SDK terrain. It's a commercial tool that's created by AGI, the company that developed Cesium itself. And it provides a quantized, it converts our data into quantized mesh data. The second one is Cesium Terrain Builder, and it provides a height map. There's a plugin called GeoServer Terrain Provider. At the time of working in this project, the plugin was not maintained, so it didn't work with the version that we were using. I think they have updated it recently. So we had to settle with the Cesium Terrain Builder. The Cesium Terrain Builder is a C++ library that is associated with the command line tools. It's developed by the Geodata Institute through the University of Southampton. It creates a tile set that sits behind any terrain server that serves this tile set, and it accepts all the GDAL supported format for elevation data. The last challenge was the burial chambers, and as I said, it's underground, so the camera needs to find a way to get in underground or under the surface, and also it's indoor. And when it comes to virtual globes, the camera position and orientation and movement is designed for a view from the top. One of the proposed solution was to use this plugin called Ground Push. The thing is also it's not maintained, and it acts a little bit funny around the edges, so even if we used it, it's not going to perform perfectly. But if you have a data that is below the sea surface, I think that's the only choice that you have to use. So the workaround that we used was to first to disable the terrain and then to move the camera inside the rooms. And the other thing that we did is that we also disabled the default navigation events, and then we have identified our own navigation events. All of this happened using the API. We didn't play or manipulate the source code. So when you have an event like the mouse move, when you look at the globe, mouse move actually pan the ground, but when you were indoor, mouse move actually makes the camera looks around. I'll do a little bit demonstration to see how the application looks like. So you have the site over here, and it actually consists of two main sites. One is Karakul, and the other is Tuekta. The Cesium by default provide, as I said, different web map services that can be viewed. You can also view your own customized imagery. And as for the vector layers, when you switch on and off, you can see the vector layers. And also it's supported by default in Cesium. When you click on any feature, the attribute table can be viewed. When you switch the 3D depiction, the terrain data is rendered, and also the 3D model is rendered. And as you can see, it sits nice on top of the terrain data because this is the terrain that it was developed on. And when you click on a building, these are the data that are retrieved and rendered, retrieved from the database and rendered. You can also edit the description and add any type of data that you can use. So the source, the crowd can actually help provide data for the model. The last feature in the application is the burial mount. And when you click it, the camera actually moves inside the room. And when you click, the camera looks around and you move backwards and forwards. When you click on the artifacts, you get to retrieve information about them. This feature was developed in the last week, so that's why it does not perform perfectly. So if we had enough time, we could have done a better job, but it works. That's it, and thank you.
You mentioned soft tourism, and I was just wondering, my own curiosity, what is soft tourism?
It actually means that visiting the place without visiting the place.
Oh, okay,
Yeah.
okay.
Yeah.
So
That's sort of
not going there and
virtually going visiting. The
it's pretty far as well,
yeah,
right?
yeah.
Okay. Have you considered then the full kind of VR experience with goggles?
Yeah, I mean, it's a little bit experimental even in Cesium itself, but they are having some work to customize this VR or AR actually. No, VR.
Yeah, I would say it's VR because you actually don't
VR,
have the you don't add to the actual environment.
Yeah.
I think that's the definition.
Yeah.
Okay. And I guess those villages have evolved over time.
Come back again.
I guess those villages, they've evolved, developed over time in those regions. Have you maybe investigated the possibility of seeing that evolve on the globe?
No, but yeah, I mean, it's one of the proposals to test the time element and to find a way to adapt the changes that happens to the region. But the focus actually comes to the images.
Mm-hmm.
Because the idea is to try to render images in different seasons, a snowy ground, and
Experience the life.
yeah, and also draw some particles to
mountains.
represent the snow and stuff like that. And in Cesium, I think it's applicable more or less.
I imagine.
Theoretically speaking. Yeah.
Yeah. Okay. Anything from the audience? You were pointing. Ah, okay, good. Okay, then thank you, Musab.
Yep.
We'll welcome Estefania. EO for Geo is your knowledge aligned with the GI EO sector demands?